Hello everyone and welcome back. In this video we're going to look at ways of describing the spread of a distribution. In the last video we discussed ways of describing the center of a distribution. However, two different data sets with the same center may look quite different. We can describe how dispersed the values are within a distribution by defining a measure of spread. The common measures we'll look at are called the range, the interquartile range, the variance, and the standard deviation. The first measure we will look at is called the range, which is the difference between the largest and smallest value in the dataset. However, just like with the mean, the range is sensitive to outliers, so the presence of outliers will have a very strong effect on the range. So we will also want to define a measure that is resistant to outliers. But first we need to define measures of position, which are called the quartiles, or more generally, they are called the percentiles. The idea behind quartiles is that we want to divide the data into quarters. So the first or lower quartile is the value such that 25% of data will fall below this value, and the remaining 75% of data will fall above this value. The second quartile is the value such that 50% of data falls below this value, and 50% of data falls above this value. And this is really just another name for the median. The third quartile is the value such that 75% of data will fall below this value, and the remaining 25% of data will fall above this value. We can generalize this division of data by defining the pth percentile, which will leave p% of data below this value. So for example, the first and the third quartiles are also known as the 25th and the 75th percentile, respectively, because 25% of data falls below the first quartile, and 75% of data falls below the third quartile. The median is also known as the 50th percentile because the median will leave 50% of data below its value. We can now define a measure of spread which will be resistant to outliers, and this is called the interquartile range. The interquartile range is the difference between the third and the first quartile, and it describes the range of the middle 50% of data. So here I've listed the steps for finding the quartiles. Note that this method will be different than what some texts or software use for calculating the quartiles and the interquartile range. There are many different ways of calculating the quartiles, but they will all be very close to each other. So let's have a look at a few examples for finding the quartile. So here is the data set in example 1.3.2, which I have written in 2 rows. Now the first step is to make sure that our data is in ascending order. The second step is to locate the median. Since we have 17 observations, then the median will be the middle value, which is 70. So this is our median. Now to find the first quartile, we want to find the median of the lower half of the data. Now the rule that we will follow is that when we're finding the quartiles, we will exclude the median from our calculations. So 70 was our median, and this value will be excluded when we calculate the first and third quartiles. So now, to find the first quartile, we will look at just the lower half of the data, which is these values here. This is the lower 50%. And now we want to find the median of this data set. So there are 8 values in the lower half of the data, which means that the median is going to be the average of the middle 2 values. And so the first quartile is going to be the average of 65 and 68. So if we take 65 plus 68, add them together and divide it by 2, we end up with 66.5. So the first quartile, or Q1, is 66.5. Now to find the third quartile, we will look at the median of the upper half of the data. So the upper half of the data are these values here, and we exclude the median from the calculations. So we have 8 values for the upper half of the data, which means the median of this data set is going to be the average of the middle 2 values. And so the third quartile will sit right in between these 2 values, and so we want to average these 2 values together. So the third quartile is going to be 75 plus 75 divided by 2, which is 75. So the first quartile is 66.5, and so this is the value that sits between 65 and 68, and it will separate the lower 25% of data with the upper 75% of data. And the third quartile, which is 75, and it sits in between these 2 values here. The third quartile separates the lower 75% of data with the upper 25% of data. So now we can use the quartiles to calculate the interquartile range. The interquartile range is going to be the difference between the third quartile and the first quartile. So we take Q3 minus Q1. We have 75 minus 66.5, and this gives us 8.5. Now let's take a look at finding the quartiles and the interquartile range for an even number of observations. Here is exercise 1.5.8, where I have written the values into 2 rows. Since there are 12 values, this means that the median will be the average of the middle 2 values. So we want to take the average of 505 and 505. So the median is going to be 505 plus 505 all over 2, which is 505. So since the median is the average of these 2 values, this means that the median is sitting in between these 2. So I'll make a line which will indicate the median. And now we can look at calculating the quartiles. So the rule was that we excluded the median from the calculations. Now because we're dealing with an even number of observations, the median is actually in between these 2 numbers. So we will include all of the values that are below this line when we want to find the first quartile, and then we will use all of the values above this line when we want to calculate the third quartile. So the first quartile is going to be the median of this data set, and since there are 6 values, we need to take the average of the middle 2, and so the first quartile is going to be 382 plus 443 all over 2, and this is equal to 412.5. The third quartile is the median of the upper half of the data. Since we have 6 values, we will take the average of the middle 2. So the third quartile is going to be 517 plus 559 all over 2, which gives us 538. Then the interquartile range will be the difference between Q3 and Q1. So we have 538 minus 412.5, and this is 125.5. So now we can summarize a data set by using what is called a 5-number summary. And they consist of these values: the minimum, the first quartile, the median or the second quartile, the third quartile, and the maximum. And we can use the 5-number summary to create another type of display, and they are called box plots. And box plots can show the center, the spread, and symmetry or skewness at the same time. So here I've listed the steps for constructing a box plot by hand, and we will go through an example so you can understand how they are interpreted. So let's construct the box plot for the average time in public transit data. So the first thing we'll write down is the 5-number summary. So the 5-number summary was the minimum, which will be 40, the first quartile, which was 66.5, the median, which was 70, the third quartile, which is 75, and the maximum, which is 95. So next we will calculate what are called the upper and the lower fences. Now note that these fences are not part of the box plot display, and they are just used to determine what are called the whiskers. So to find the upper fence, we will take the third quartile and add 1.5 times the interquartile range. So the third quartile was 75. We add this to 1.5 times the interquartile range, which we calculated to be 8.5. And this gives us 87.75 as our upper fence. The lower fence is the first quartile, subtract 1.5 times the interquartile range. So we have 66.5 minus 1.5 times the interquartile range, which was 8.5, and this is 53.75. So now, any value that are above the upper fence, so any value which are above 87.75 are outliers. So the upper fence is 87.75, and there are two values that are above the upper fence. So this means that the outliers are 90 and 95. Now values that are below the lower fence, so values that are below 53.75, are also outliers. So if we look at our data set, we have one value that is below 53.75, which means that this is an outlier. So now we can use the upper and lower fences to determine the whiskers. So the whiskers are the most extreme value that falls within the fences. So to find the right whisker, we want to look for the most extreme value that falls below the upper fence. So our upper fence was 87.75, and that sits in between 85 and 90. The most extreme value that falls below the upper fence is 85. And so 85 is our right whisker. To determine the left whisker, we want the most extreme value that falls above the lower fence. So the lower fence was 53.75, which sits in between 40 and 60. And the most extreme value that falls above the lower fence is 60. And so 60 is our left whisker. So now we can construct our box plot. Box plots can be drawn horizontally or vertically, and for this example we will draw it horizontally. So we will first draw a horizontal measurement scale that spans the range of the data. Next, we will draw a rectangular box where the edges are at the first and the third quartile. So the first quartile was 66.5. So we'll draw a vertical line at 66.5. And the third quartile was at 75. So we'll also draw a vertical line at 75. And this will create our box. Next, we will draw a line segment inside of the box, which is located at the median. The median was at 70, so we'll draw a vertical line inside of the box at 70. So now we will draw line segments from each end of the box to the whiskers. So we calculated the right whisker to be at 85. So we'll draw a line that connects the edge of the box to the right whisker. And our left whisker was at 60. So we'll draw a line segment from the edge of the box to 60. Now, values that are outside of the fences are marked, typically with an asterisk. And so we found that the values 90 and 95 were outliers. So we'll draw an asterisk at each of these values. So 90 and 95. And these denote the outliers. And we also had an outlier at 40, so we also have an asterisk at this value. So this is the box plot for the public data set. So we'll call this the box plot of average time in public transit. Okay, and along the horizontal axis, this is time, which is measured in minutes. Now recall that the interquartile range was defined to be the difference between the third and the first quartile. So the interquartile range can be represented by the length of the box. So the length of this box here is the interquartile range, the difference between Q1 and Q3. There are certain features that we can look for in a box plot to determine whether a distribution is symmetric or skewed. If the median is in the center of the box and the whiskers are relatively the same length, then the distribution is symmetric. If the median is to the left of center and has a longer right whisker, then the distribution is skewed to the right. And if the median is to the right of center and it has a longer left whisker, then the distribution is skewed to the left. So if we look at our box plot that we drew here, what we see is that the median is to the left of center and it has a longer right whisker. And so this tells us that the distribution is slightly skewed to the right, since the median is slightly left of center and it has a longer right whisker. So now we will look at two very commonly used and closely related measures of spread, which are called the variance and the standard deviation. The variance is the average square distance between each observation and the mean, and the sample variance is given by this formula. So it is the sum of y sub I minus y bar squared all over n minus 1, where y sub I are the observations, y bar is the sample mean, and n is the sample size. Then the standard deviation is the square root of the variance. So why do we want to take the square root of the variance? Well, it's because the units for variance will be in the square units of our observations. And we typically want to work with the same units as the observations, which is why we take its square root, which is called the standard deviation. And the standard deviation will measure how far typical values will deviate from the mean. And just like with the mean, the standard deviation will be sensitive to outliers. So note that the standard deviation and the variance are non-negative values. So we will always take the positive square root whenever we calculate the standard deviation. So let's take a look at calculating the variance and standard deviation for this data set. So here we have four values, which are 1, 3, 5, and 7. And I've created a table to help organize the calculations. Now the first thing that we need is to calculate the mean. So the mean is 1 plus 3 plus 5 plus 7, all divided by 4. And this gives us a value of 4 for the sample mean. Now that we have the sample mean, what we'll do next is to take every observation, yi, and subtract the mean. So 1 minus 4 gives us negative 3. 3 minus 4 gives us negative 1. 5 minus 4 gives us positive 1. And 7 minus 4 gives us positive 3. So now what would happen if we were to add up all of the deviations from the mean? So if we were to add up all of the values in this column, what we would get is negative 3 plus negative 1 plus 1 plus 3. And this will give us a value of 0. And this will always be true. The sum of the deviations is always equal to 0. And this is partly why we want to square the deviations so that we make all of the differences to be a positive value. So now in the next column, we want to square the deviations. So we want to take negative 3 squared, which gives us positive 9. We take negative 1 squared, which gives us positive 1. We take 1 squared, that gives us positive 1. And we take 3 squared, which gives us positive 9. And if we add up all of the squared deviations, this will give us a total of 20. So the value of 20 is the sum of the squared deviations. So in other words, it is the numerator of the variance formula. And then to calculate the variance, we take this value and divide it by n minus 1. And so the sample variance is going to be the sum of the deviations divided by n minus 1. So we have 4 observations in our data. So that gives us 20 over 4 minus 1, which is 6.67 rounded to 2 decimals. So that is our sample variance. And we can now calculate the standard deviation as the square root of the variance. So we take the square root of 6.67, This gives us 2.58 rounded to 2 decimals. And this is our standard deviations. Now the calculations for the variance and the standard deviation are quite tedious, and if we had hundreds or thousands of observations, then performing these by hand would be very cumbersome. So these calculations are often left to technology instead. Now we can look at choosing a summary when we're given certain types of distributions. So first, we will want to graph the data using histograms or box plots. Then if we notice that the distribution is nearly symmetric, then we can use the mean and the standard deviation as the measures of center and spread. And if the distribution is skewed, then we want to use the median and the interquartile range as the measures of center and spread. And this will conclude our lesson for this video. In the next video, we will look at comparing and transforming distributions, and I'll see you all then.